All right, so this is part 2 of our derivation of the D6d character table. So in the last video, what we figured out was that we had 24 symmetry operations in this point group, and that we can group them, or that we ought to group them, into 9 classes. And so those classes are, well, you always start with the identity class, just sort of by convention. And then there's the principal rotation axis is a 2C 6 class that contains C6 and the C6-5 operations, which are mathematically equivalent. But there's also a 2S12 class, and these are kind of so improper rotation axis of a higher order. These are kind of funky point groups. In their rare example where you have an improper rotation axis that's actually greater than the principal rotation axis. So by convention, in these cases, you actually put the one with the highest n first. So it's the true principal rotation axis is actually this S12. It's an improper rotation axis. And then we have 2S4, and these are in sort of arbitrary order, but we'll put this one first just so it's easy to track our Mulliken symbol rules at the end when we name our irreducible representations. It doesn't really matter what order you do this, but this is just the order that is seen in most character tables. And then so we have our other classes here. Our C2, that's coincident with the principal rotation axis. And then we have 6 perpendicular C2s. Remember, we have n perpendicular C2s in a D point group. So we have D6 point groups. So we have 6 perpendicular C2s. That also gives us, for D point group, 6 dihedral mirror planes. So we have 9 classes here. That tells us we're going to have 9 irreducible representations. So we'll label these gamma 1 through 9 just as placeholders, and then eventually we'll put down the Mulliken symbol values for these but we only can know what to call them once we actually derive what those irreducible representations are. So gamma 1 is an easy one. It's a freebie. So they're totally symmetric representations. Ones across the board. We're always going to have that for every single character table. Moving on from there, first thing I like to do is test different linear functions. So I'll test the z function. And I'll draw out, and remind us how we always do this. We have x, y, and z. We can define x and y however we want, as long as x, y, and z are all perpendicular to each other. But z has to be coincident containing that principal rotation axis. So that C6 or that S12. I'll just put the C6 for simplicity here. Remember the S12 is a C12 followed by a sigma h, a flip horizontal mirror plane. We'll be going over that a lot as we do this derivation. All right, so then what we're doing is we're asking the question, hey, how does this z vector that we're testing, this function, this linear function, represented by a z vector, how does that transform across all these different operations, or at least one class in all those operations? We can choose any operation that we want. The way that this works is that for identity, well, the z vector goes into z because identity does nothing. And then we can think about the 1-by-1 matrix that represents this transformation. We take the trace of this matrix and we call the trace, or the character, that's why it's called character, the sum across the diagonal of this matrix. So the character for this transformation of the identity is just equal to 1. There's only one element there, so that's all we're adding up is 1. So we got a 1 here. And, we don't know what's going to happen with the z a priori. It could transform as gamma 1, but we're going to keep track of it, and hopefully it'll transform as something different. Therefore, we can call it something, it's a true gamma 2. So then we go for the S12. And the S12, remember, is, as we said just a moment ago, an S12 operation is a C12 followed by a sigma h. A sigma h, in this case, right, is in the xy plane. It's horizontal to the z vector. So what's going to happen? Well, first we do a C12. We're rotating the z vector by 30 degrees. if we rotate by 30 degrees, that z vector is still pointing up. But then if we do a sigma h, a flip, we are the vector is looking at itself in the mirror plane. So we end up flipping this z vector into the negative itself. And when we do that, the 1 by 1 matrix that describes z going to negative z is multiplying by -1. And so the sum across that main diagonal, well, there's only one element, it's a 1 by 1 matrix, for the S12 transformation is -1. So we got a -1 here, so we know we're different than the positive one we got before. So we're on our way to deriving a new irreducible representation or a new vector S12. All right, so next we just move right along. We do the C6. The C6 is not going to have this mirror plane, right? All it is a C6. It's a 60-degree rotation. The z vector is going to go to z. And just like for the identity operation, that means we're going to have a1. Okay, so moving right along, our next symmetry class is the S4. S4 is very similar to the S12, right? It's equal to C4 followed by sigma h. At this point, we know any rotation across the z-axis doesn't do anything. So that C4, that 90-degree rotation, isn't going to do anything. But we do have that sigma h, and that's going to effectively get us z to minus z. And if that's true, we know it's just the same case as the S12 case, and so we're going to get a value of -1 up here. Moving right along, we have the C3 class, the 2C3 class, that's just a rotation, so z is going to go to z. So we get a value of 1. And then we have an S12 5 times. That's equal to a C12 5 times, followed by sigma h 5 times. But sigma h 5 times is an odd number of flips, so it's just sigma h 1 time, equivalent to that. And so again, this rotation doesn't do anything, but the sigma h does. And so we get z going to negative z. And so we're going to get -1. A C2 is just a rotation. So we're going to get z go to z. And then we have these perpendicular C2s. And we have 6 of them. And so we can choose to define one of them to be coincident with the x-axis. And if we do that, then it's very easy to visualize how if we rotate along this x plane, we are going to get a value of around this x-axis. We're going to be flipping that arrow 180 degrees, right? Rotating 180 degrees. So we're going to go positive to negative. We're going to get z going to negative z for a C2 prime. And then our last one is just to look at a sigma d. And the important thing here is to remember that the sigma d contains, all the sigma d's contain the z vector. The sigma d's are actually going to bisect two perpendicular C2s. That's why they're d's and not v's. Vertical mirror planes, they're not. They are dihedral mirror planes with a d. But that doesn't actually really matter in this case. We don't have to visualize that. We just need to know or recall that dihedrals and vertical mirror planes both are similar in the sense that they both contain the principal rotation axis. And if they contain the principal rotation axis, that means that z is going to go to z, right? Because the vector is in the mirror plane. And so with that, we relatively quickly derived our first irreducible representation. And so from here, the next one that we'd like to do usually is do x, right? And so we go through the same process, but now not with a z vector, but we're going to test the x function. And so I'm going to draw an x function just to help us visualize that, just like the z function, except it's coincident with the x-axis now. And we're going to ask the question, hey, how does the x-axis transform with each of these symmetry operations? And we start with our first symmetry class, which is our identity class. So if we do anything to identity on anything, we get back itself. So x is going to go back to x. And if we go ahead and now do an S12, which is the next one, we know again that S12 is a C12 followed by sigma H. Remember the sigma H, S12, I'll just write that out again. C12 followed by sigma H. The sigma H, remember, is horizontal mirror plane. That's what the H means, to the z-axis. And because the x vector and also the y vector, which we're going to have to do in a second here, are in this mirror plane, they're not going to do anything. Anytime you have a vector in a mirror plane, it's not going to change how it transforms. And so effectively, this just becomes a C12. And so now we have to actually use the rotation matrix. And so the rotation matrix is a 2 by 2 matrix that tells us how XY transforms when we rotate it, either clockwise or counterclockwise. It doesn't really matter how you define things here. But the standard form that people typically use doesn't, again, it makes no difference mathematically. Nice thing is the trace of the matrix will always come out to be the same thing. But you're going to do a cosine of 2 pi over 12, right? So it's 2 pi over n, what you're rotating, and you have a C12 here that you're doing. So you get cosine 2 pi over 12 minus sine 2 pi over 12 is your next element of this 2 by 2 matrix. And then you have a positive sine 2 pi over 12 and a cosine 2 pi over 12. These, of course, all these 2 pi over 12s can, of course, be simplified to pi over 6. You end up taking the trace of the matrix, and you're just going to get 2 times cosine pi over 6, which is root 3, right? Because cosine of pi over 6, you may recall, is root 3 over 2. And so if you have root 3 over 2 plus root 3 over 2, that's our character, our chi, right, of S12, that is going to be equal to just root 3. And so under here, the S12 function, we actually, S12 class under gamma 3, we have to put root 3. Pretty interesting that we don't get an integer value, but there's nothing in the character table rules that tells us we need to have integer values. They are a little bit more rare to have non-integer values, but a lot of times you will get non-integer values. And in other videos, I show you cases where we get imaginary or even complex numbers as our values. But more importantly, what this tells us at this point is that x cannot be, that how x transforms with the S12 operation cannot be explained simply in terms of x, right? It doesn't go just into x or negative x. It goes into a linear combination of basically x goes to cosine 2 pi over 12x minus sine 2 pi over 12y, and y goes to sine 2 pi over 12x plus cosine 2 pi over 12y. That's what this matrix, rotation matrix, does for us. That tells us, in other words, that x and y vectors transform together. And whenever you have two functions that transform together, your dimensionality, your character under the identity has to be equal to 2. And the reason why is because x goes to x, y goes to y with the identity operation. And so you have the identity matrix that explains this mathematically. And then you take the trace of this matrix, the sum across the diagonals, and you're going to get 2. 1 plus 1, right? The character is going to be 2 there. So that's why we have a 2 there. We have an interesting root 3 there. Now we move on to C6. C6, well, it's just a 60 degrees of rotation. So again, we use our rotation matrix. Now it's not going to be 2 pi over 12, but it's going to be 2 pi over 6, which is, of course, 2 pi over 3. But everything else with our formula stays the same. And so now your value here, well, cosine 2 pi over 6 or cosine pi over 3 is equal to 1/2, right? And so chi of C6 is equal to 1/2 plus 1/2, which is equal to 1. All right, so our character for this class is 1. Then we move on to the S4 class. S4, remember, is a C4 followed by sigma H. But we talked about this extensively, how sigma H doesn't do anything to the X or the Y vectors. We now know that X and Y transform together. We could use the rotation matrix here, or you could just think about how X transforms when we do a 90-degree rotation. X is going to go, with a 90-degree rotation, into Y. And if we have a Y vector, Y is going to go into 90 degrees and go into negative x. So we got x going into y and y going into negative x. We're spinning this across the z-axis, remember? And so when we write our matrix, we get off-diagonal elements now. It looks like this. That explains how x, y goes into y and negative x. And I just accidentally deleted everything, so I'm going to have to rewrite things here. So give me a second. So we have the character there be for S4, we basically figured out that x went into y went into negative x. So we had this with transformation, and we had the trace of this matrix. This is for the S4 operation, equals 0 plus 0, which equals 0, so we can put a 0 up here for the S4. All right, our next one is the C3 class right here, so we just march right around along. We do a C3 rotation on the x vector and the y vector. We get cosine 2 pi over 3, negative sine 2 pi over 3, sine 2 pi over 3, cosine 2 pi over 3. And so the cosine of 2 pi over 3 is negative 1/2. So when we take the trace of this matrix, we get that the chi, this is for C3, is equal to negative 1/2 plus negative 1/2, which is equal to negative 1. So this is negative 1 right here. All right, next one, we have an S12, 5. S12, 5 is equal to, remember, C12, 5, followed by sigma h 5 times, but it's an odd number of flips, odd number of horizontal mirror plane operations, so it's equal to sigma h, but as we talked about many times before, both the x and the y vectors here are in the mirror plane of the sigma h, so the sigma h doesn't do anything. So all this is an x y is a C12 5 times rotation. So that's going to be equal to, well, it's a 2 pi over 12 rotation. So this is now going to be equal to not 2 pi over 12, but 5 times that, because we're doing it 5 times. So it's going to be a 10 pi over 12 rotation. And we can put that 10 pi over 12 term in all aspects of our 2 by 2 matrix. And now we take the trace across this matrix. Of course, 10 pi over 12 is the same as 5 pi over 6. Cosine of 5 pi over 6 is negative root 3 over 2. So we get negative root 3 over 2. The trace of the matrix is sum across the diagonals. Negative root 3 over 2 plus negative root 3 over 2 equals negative root 3. All right, and then we have a C2. And so C2, we do a rotation here. And this is a rotation, this is a C2, still this C2 is equal to basically a C6 3 times. It's a 180-degree rotation. So if you envision what that does, it's going to spin around the z-axis still. So it's going to take x into negative x, and it's going to take y into negative y. And so for C2, we're basically thinking about what matrix gives rise to these transformations. That's negative 1 on top of the diagonal. So I have negative 1 plus negative 1 equals negative 2. Okay, and then we have a C2 prime. For the C2 prime, we can define one of these C2s as we did, well, we have to define it as we did before, which is one of the C2 primes we defined as being coincident with the x-axis. And so when we do this, we're rotating something 180 degrees along the x-axis, but we're rotating along that axis is not going to change anything. So this is one of the C2 primes in the C62 prime class. That's going to take x goes to x. But we're off axis for the y, and so that's going to flip y into negative y when we're rotating that way. And so that gets us x going to x, y going to y. And so x, y goes to 1, negative 1, 1, 0, 0, negative 1. And so the chi of C2 prime is equal to 1 plus negative 1 equals 0. Sigma d. Sigma d is a top form to visualize. And the reason why is because you have 6 C2s, and all the sigma d's are going to be off axis because the sigma d's bisect the C2s. And so the 6 C2s are going to be what, 30 degrees apart from one another. And so the sigma d's are going to be 15 degrees off from that. So bisecting the C2s. So you can work through the math here. I recommend at this point just using the principle of orthogonality to figure out this last component here. We know that gamma 1 dotted with gamma 3, gamma 2 dotted with gamma 3 has to equal 0. Gamma 1 is the best one to look at because it's ones across the board. And these dot products, remember, are always normalized to the number of operations in each class. And so because gamma 1 is all equals 1s, basically it's just 2 times, we'll put this as an unknown alpha. It's 2 times the number of operations in each class plus root 3 times the number of operations class, etc. So we're going to get 2 times 1 operation in the symmetry class. Let me rewrite that, a little messy there. Plus root 3 times 2, right? 1 times 2 plus 1 times 2 plus 0 times 2. Not even going to write that one because it's 0. Plus negative 1 times 2 plus negative root 3 times 2 plus negative 2 times 1 plus 0, don't have to worry about it, so plus alpha. And all that has to equal 0. That's our dot product. We'll have a 2 and a negative 2. Those cancel out. We have a negative 2 root 3 and a positive 2 root 3. Those cancel out. And we have a 2 and a negative 2. Those cancel out. So alpha, therefore, has to be equal to 0. And so this value, very quickly, we figured out equals 0. A lot easier way than other methods that we could have used. Okay, and then at this point, we've done x, y, and z. And so let's stop here and we'll start looking at other functions to derive the, most of the remaining 6 irreducible representations. So we can finish this all up in the next video.